Friends, welcome to our YouTube channel Pro Pulling Rabbits Out Our Hat, a brand new math, physics, science channel. Okay, let's go into the episode 0, the limit of logarithmic patience. Do you believe this, friends? Something must be equal to something. Okay, then let 1 be equal to 1. And we can write 1 as a real number power some other real number which approaches 0. So here we write it thus. Limit epsilon goes to 0, x power epsilon is equal to x power epsilon. That's a harmless, simple looking equation. Okay. And also, logically, we can do same operations on both sides of the equations. And let us take natural logarithm on both sides, on right hand side and left hand side. So ln x power epsilon is equal to ln x power epsilon, taking the limit epsilon goes to 0. So now comes the magic. As natural logarithm ln is the inverse function of exponential operation, we can write x power epsilon is equal to e power ln x power epsilon, limit epsilon goes to 0. That's the definition of natural logarithm, friends. Okay, time to apply power rule for logarithms on RHS. So we apply this cute little rule called power rule for logarithm. Whereas if the argument of logarithm has a power in it, we can move that power in front of the logarithmic operation. So now we write limit epsilon goes to 0, x power epsilon is equal to e power epsilon ln x. But note there exists a series expansion for that e power thing on the right hand side, and that's called exponent series. According to exponent series, we can write e power epsilon ln x as 1 plus epsilon ln x by 1 factorial plus epsilon ln x square by 2 factorial plus epsilon ln x cube by 3 factorial plus so on. So we shall derive this expression later, some other time in our channel. And now we are going to keep only the constant term and the linear term in the series. Why? Other terms approaches 0 very quickly than the linear term. So we just jettison them off and ignore them. And also life will not be that interesting if you don't ignore other terms. Okay, also there is a murky thing in calculus called epsilon delta mumbo jumbo. But they need not to blame the mathematician Cauchy for it. He only used it, never defined it. He made a calculus a very strong thing with a rigor. He has that fan. Okay, back to our main story. With this approximation, the BLUISH equation becomes x power epsilon is equal to e power epsilon ln x, limit epsilon goes to 0. Now the right hand side becomes 1 plus epsilon ln x, and we are going to apply the principle that we can do the same operation on both sides. That means we subtract 1 and divide by epsilon on both sides, and that is admissible. After the rearrangement, we finally arrive at voila, limit epsilon goes to 0, x power epsilon minus 1 divided by epsilon is equal to ln x. But RHS does not contain any epsilon. So let's keep the limit on the LHS only. So we have this beautiful definition for logarithmic function, natural logarithm. Ln x is equal to limit epsilon goes to 0, x power epsilon minus 1 by epsilon. So that's a cute definition for logarithm in terms of some limit expression. So this we call our little gem. We have pretty out a fat funny out of an empty hat, nothing more than 1 is equal to 1. And that's cute. Okay, let us check, does this work? Yep, let's experiment. For x is equal to 0, ln 0 is equal to limit epsilon goes to 0, 0 power epsilon minus 1 by epsilon is equal to limit, okay, 0 power epsilon, we call, for the time being, we make it 0, then 0 minus 1 by epsilon. Now we make epsilon 0. That's not that admissible, that's not rigorous, but okay, let's do that thing. And that becomes is equal to minus infinity. Okay, of course. Natural logarithm or logarithm of 0 approaches minus infinity. You might check for it. E power minus infinity or anything power minus infinity goes to 0. So that worked for the extreme case 0. Don't cry foul. I am a physicist, not a mathematician. Yeah. Not that much rigor here. Okay. Let us check for x is equal to 1. That also works. Ln 1 is equal to limit epsilon goes to 0, 1 power epsilon minus 1 divided by epsilon. Limit epsilon goes to 0, 1 power epsilon minus 1 divided by epsilon is equal to, oh, I have repeated that thing. Okay, not bad. Is equal to 0. 1 power anything 1 minus 1 0. So we have this 0 by 0 indeterminate, but okay, for the time being, believe that it is 0. Okay, let us check for other values. So we still have our suspicions. Let us find natural logarithm of 2 in this way. Let us assume epsilon is equal to 0.1 first. So natural logarithm of 2 becomes approximately equals to 2 power 0.1 minus 1 divided by 0.1, and that becomes, okay, you can use your calculator and check that, and 0.7177, not bad compared with the exact value 0.6931. Okay. But wait, epsilon should approach 0. Here are the values of natural logarithm of 2 calculated for various epsilon up to 4 decimal places. So here you can see a beautiful table, and we make epsilon goes to approach 0 gradually, 0.1, 0.01 logarithmically, I must say, 0.001, 0.0001, 0.000001, and you can see on the last column the percentage of error in calculating natural logarithm of 2. And that falls very softly, and the last column of last entry is 0.007, that not 7, James Bond error percentage. Okay, that's cute. So now for some curves, the percentage error decreases approximately linearly as epsilon approaches 0, as you can see from this beautiful little plot. So here you can see a pretty close animation, that plot x for epsilon minus 1 by epsilon as epsilon approaches 0, approaches ln x closely. Also it approaches negative infinity for epsilon values approaching 0. Okay, let's play with our expression that we have derived so far. First, we shall derive a series expansion for the natural logarithm to show the potential of our little gem. So what's a series expansion? We have already seen this for the exponential function, if you remember correctly. It is just a power series in x, the independent variable, with characteristic coefficients. For an example, if we have f of x as our function, f of x is equal to a0x power 0, a1x power 1, plus a2x square plus so and so, ax power I, and so on. It goes on. It might be finite or infinite series, if you care. So here a0, a1 and A2 and so on, so are characteristic coefficients of the series expansion. And the hardest part of series expansion in finding a series expansion is determining these characteristic coefficients. So we should also ensure that with these coefficients the series approaches a finite value, and there are convergent tests, many of them discovered by Cauchy. Okay, that involves some technical details. We shall see them in future. Okay, let us forget technical details for a while and focus on our aim. Say ln x is equal to this power series expansion a0 x power 0 plus a1 x power 1 plus a2 x square plus a3 x cube plus so and so a x power I plus so and so. But there is a glitch. If we put x is equal to 0, our series should be infinity. But ln 0 is equal to a0 0 power 0 plus a1 0 power 1 plus a2 0 power 2 plus so and so. 0 power 0, nobody knows better. What is 0 power 0? We can let the power approach 0 from positive side or negative side, depending on that would have a value. Okay. So to circumvent this nasty glitch by climbing, we are interested in deriving an expansion for ln 1 plus x rather than for ln x. We can do that. Now comes the time for our jump. We are going to apply our jump right here. Ln 1 plus x is equal to limit epsilon goes to 0, 1 plus x power epsilon minus 1 divided by epsilon. Okay. Now we can expand 1 plus x power epsilon for x value, absolute value of x less than or equal to 1 using the thing called generalized binomial expansion discovered by Isaac Newton, the great Sir Isaac Newton. So we are going to use it right now. So in future episodes we shall also derive this binomial expansion, generalized binomial expansion. We shall do all that. Okay. Only thing that you have to keep in mind is that binomial expansion works only for absolute values of x less than 1. Generalized binomial expansion. Otherwise the series diverges simply. Okay, let's do it. Substituting the binomial expansion in the limit equation, we have limit epsilon goes to 0, 1 plus epsilon by 1 factorial x power 1, epsilon minus 1 by 2 factorial x square, plus epsilon minus 1, epsilon minus 2 divided by 3 factorial x cube, plus so and so minus 1. Okay, now that minus 1 here and plus 1 there nicely cancels out. We have a limit epsilon goes to 0, epsilon by 1 factorial x power 1 plus, okay, so on. That series other than cancelled out 1 divided by epsilon. So now in the upstairs, in the numerator, we take out epsilon, which is common in all terms, and here in the downstairs, in the denominator, there is an epsilon also. We cancel them out both. So now we have ln 1 plus x is equal to 1 by 1 factorial x power 1 plus epsilon minus 1 by 2 factorial x square plus epsilon minus 1 epsilon minus 2 by 3 factorial x cube. But now, voila, we don't have any epsilon in the numerator, and denominator. So we can, without any guilty feeling, we can directly put epsilon is equal to 0. So if we put directly epsilon is equal to 0, our series becomes 1 by 1 factorial x power 1 plus 0 minus 1 divided by 2 factorial x square plus 0 minus 1, 0 minus 2 divided by 3 factorial x cube plus 1. So now we can cancel some terms out. After cancelling out terms, our series becomes ln 1 plus x is equal to x minus x square by 2 plus x cube by 3 minus x power 4 by 4 plus an alternating sign series. Okay, that's cute. We have pulled another rabbit out of a hat. Okay. So now we can see in this plot the convergence and divergence of log series. The log series that we have derived converge within this limit x greater than minus 1 and less than or equal to plus 1. Okay, that's within that limit, narrow limit, but it works there. Out of that limit, the approximation is not good. The series diverges to infinity. Okay, so we have derived an expression for ln, the natural logarithm function. Let us use it for to derive an expression for series expansion for natural logarithm of 2. Okay, ln 1 plus 1 is equal to ln 2 is equal to 1 minus 1 by 2 1 square plus 1 by 3 1 cube minus 1 by 4 1 power 4 so on so. So now if we do the math, we have ln 2 is equal to 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus, that's harmonic series. The sum of reciprocals of all natural numbers only with alternating signs. The beauty is that converges, whereas the harmonic series diverges. We shall prove it also. Okay, so we have a simple and elegant result, and the series slowly converges to 0.6931. You might check with your calculator, or you can write a Python program if you have patience. Okay, no problem. So now the added bonus, another added bonus, that is added bonus 2. Harmonic series diverges. We shall prove it. So harmonic series is the sum of reciprocals of all the natural numbers. But you might have a feeling that as the terms of harmonic series are monotonously decreasing, the series must have a finite sum. But that's not so. And it diverges to infinity. And that's a bit counterintuitive. So let us prove it somewhat informally using our expansion formula. Formula. Yeah. Expansion for ln 0 and harmonic series diverges. We are violating our own rules. We are going to expand ln 0. We substitute x is equal to minus 1 in our expression. We have ln minus 1 plus 1 is equal to ln 0 minus 1 minus 1 by 2 minus 1 square plus 1 by 3 minus 1 cube, so on. So we take that minus 1 out. We have ln 0 is equal to minus 1 multiplied by, look there. That's our harmonic series. 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, so on so. So ln 0 is minus infinity, if you remember well. So we have minus 1 multiplied by our harmonic series. 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 must be equal to infinity. There is no other way. That proves our casted harmonic series diverges to infinity. But I remember telling you there is a problem for expansion of ln 0. Please forget it. We have circumvented now. Yeah. Okay. So now we are going to disintegrate ln x. Don't bother. By disintegration, I mean differentiation. So what is the differential of ln x with respect to x? So by the definition of a differential, limit delta x goes to 0, f of x plus delta x minus f of x divided by delta x, and that is the differential of f of x. And this definition is due to Cauchy, I believe. So the differential of ln x is given by limit ln x plus delta x minus ln x divided by delta x. Now we use our limit definition on the RHS, and we have double limits now. Oh, limit delta x goes to 0, limit delta, not delta, epsilon goes to 0, x plus delta x power epsilon minus 1 by epsilon minus limit epsilon goes to 0, x power epsilon minus 1 by epsilon over delta x. So we are going to find the limit of our fashions. So now we are going to do something called playing the double limit, the art of double limit. And if you do some math, simple algebraic operations, this minus 1 and that minus of minus 1 cancels out. So now we have x plus delta x power epsilon minus x power epsilon divided by epsilon in the numerator and delta x in the denominator. So now the differential of ln x becomes limit epsilon goes to 0, limit delta x goes to 0. Now we did a trick in the upstairs. We have pulled out x power epsilon from the x plus delta x power epsilon. So if we do that, we have x power epsilon 1 plus delta x by x power epsilon minus x power epsilon divided by epsilon over delta x. Excuse me. And if we expand 1 plus delta x by x power epsilon using GBT and neglect higher order terms, we have x power epsilon within brackets 1 plus epsilon delta x by x minus x power epsilon over delta x, and we then multiply into the brackets to have x power epsilon plus x power epsilon delta x by x, and there is a minus x power epsilon also, so we cancel them out simply. And so we have now this double limit thing, limit epsilon goes to 0, delta x goes to 0, x power epsilon delta x divided by epsilon delta x, and there we cancelled our epsilon delta x thing. We have not substituted 0 yet, but look, we don't have epsilon and delta x for troubling them. Troubling us. So we can simply put epsilon is equal to 0 now without much trouble, and that becomes x power epsilon is equal to 1. So we have finally d by dx ln x is equal to 1 by x. So we have finally that. That's the differential of ln x, if you remember from your textbooks. So we have disintegrated the natural local now. It is sad, and let us integrate it again. So integrating ln x using the limit definition, we are going to do that, not the textbook way, usual way. So integral of ln x is dx is equal to limit epsilon goes to 0, x power epsilon minus 1 by epsilon dx. So now we have exchanged integral with limit. That's not rigorous mathematics, but that can be done. They are linear operators, taking limit and integration, linear operators. So we can exchange them. So now integral of ln x dx becomes limit epsilon goes to 0, and we have applied our integration within the square bracket separately. Integral of x power epsilon by epsilon dx minus 1 by epsilon integral of 1 by epsilon dx. Okay, here continues our little derivation, and integral of x power epsilon dx minus integral of dx. We have pulled out the common 1 by epsilon factor out. So now the right hand side becomes a limit epsilon goes to 0, 1 by epsilon, and x power epsilon can be simply integrated to, if you remember our integral tables, that is the most fundamental integral. X power epsilon plus 1 divided by epsilon plus 1 minus x. And now we do some math. We multiply the x second term by epsilon plus 1 and divide it by epsilon plus 1. So the value won't change. X power, that becomes x power epsilon x multiplied by x minus epsilon x minus x divided by epsilon plus 1. So now we have, we are dividing by epsilon the numerator. We have moved that 1 by epsilon thing in the numerator to the numerator. So now that has become, we have pulled out x from x out of common terms. So x power epsilon minus 1 minus epsilon x divided by epsilon plus 1. There we have divided out individually, that means separate terms. X power epsilon minus 1x divided by epsilon minus epsilon x by epsilon. So that epsilon cancels out nicely, and now we apply a limit to every individual terms on the numerator and the denominator. So you can already see where we are getting, and that the limit epsilon goes to 0, x power epsilon minus 1 by epsilon is equal to ln x. That's the gem that we have derived. Limit epsilon goes to 0 x, no business for epsilon here, so that remains x. Limit epsilon goes to 0, epsilon plus 1, just put epsilon is equal to 0, we have 1, that's all. Surprise! Integral of ln x dx is equal to x ln x minus x. Did we forget something? We forgot those infamous constants in integrations without limits. No, not that limit we have applied, but those which ride on the integral sign. So this is not a definite integral, an indefinite integral. We must add a constant, and we naturally name that constant c. Surprise! So finally we got that. So hope you have enjoyed a bit of easy mathematics. You can relate to me in the awe I feel how so much can be derived from so little. We have just begun from 1 is equal to 1. But we had a background knowledge, and that made us so powerful. Applying so many things like binomial expansion, expansion for exponential series, e power series, and we have applied. Okay. But those things can also be derived from very fundamental things. So we shall do it in our future episode. We shall play with it in future episodes. This channel is mainly for beginners, and initial stuff will be at some basic but interesting level. We shall get sophisticated as time passes. Don't bother. We shall have some historical stuff also. So now I'm blaming for epsilon theta formulation of limits. Cauchy, the origins of Cauchy's rigorous calculus. You have to read this wonderful book by Judith V. Graffiner. I shall post a link if you care to buy the book. No, sir, we are all indebted. We are all indebted to Cauchy for formally putting calculus, the mathematics of calculus, on a rigorous level. We are all indebted for that. So in future episodes, it's going to rain math and physics. So brace yourselves. logic and set, trigonometry, complex analysis, differential equations, number theory, real analysis, calculus, property and statistics, data science, numerical analysis with Python and Java, classical and quantum dynamics, microcontroller programming, and etc. 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 It does not stop there. Lot of topics, but time is limited. Earth is long, life is short, they say. So please subscribe, click the bell icon, and patronize. In future episodes, we are planning to begin from the beginning. That is from the natural numbers from the time of Stone Age. No, Stone Age. Not Stone Age. Stone Age. You. Okay. Stone Age. Then we shall jump on for the algebra and trigonometry, calculus, complex analysis, etc. shall be in waiting. Then slowly we shall mix physics, science, art. Thank you. Our next episode is A Tale of Stone Counting, Numbers Naturally Yours. So here we have a nice little quote from Paul Alois. I don't know how to pronounce this great mathematician's name, but that doesn't count much. A mathematician is a machine for turning coffee into theorems. Yes, yeah. Sometimes we turn tea into theorems also. Thank you for watching.